Okay. I had to sort of end a little bit suddenly that last video. But the idea there, right, is, your linear equations, you're kind of running through that strategy to solve them. And in the end, you should just like end up with a number, x equals any value, positive or negative. Could be a whole number, could be a fraction. I think in both of those last examples, they ended up as whole numbers, but that's a little bit unusual, especially if we're just sort of pulling numbers out of a hat. I would say you're much more likely to get some sort of positive or negative fraction from a linear equation. Sometimes the book will, on purpose, give you a little bit of a nicer problem that ends up as a whole number. But if you get a fraction, it's not a big deal. It just is what it is, and that's totally fine. The other thing that can happen, and there are sort of two, I guess what I'll call unexpected solutions, sort of two unexpected cases that can happen when you're trying to sort of solve these equations. And I think the best thing to do is probably just sort of start two examples and just sort of show you what it's going to look like when you kind of encounter them when you're solving these problems. So let's just sort of start with two more equations. Let's do 3 times the quantity x minus 4 equals 2 times x plus 6, plus 1x, right? Plus x. So simple enough, right? This looks pretty similar to what we've been doing. So let's distribute to start. 3 times x, right? 3x minus 3 times 4, so minus 12 equals, distribute on the right, 2 times x, right? 2x, 2 times 6 plus 12, and then plus x. So not particularly long, not really huge values here. So we've distributed, let's look for any like terms on each side. This is just a 3x and a minus 12, so they won't combine. On the right, we do have 2x and then this sort of plus, what would be 1x. So that would be a 3x also. So my right-hand side here looks like 3x plus 12, and my left-hand side looks like 3x minus 12. This might be the point where you're saying, well, that's kind of interesting, and this is sort of a 3x minus 12 and a 3x plus 12. That seems a little funky because this is sort of 3x and 3x, but then it's plus and minus on the 12s. If these guys are supposed to be equal to each other, in theory 3x should equal a 3x, right? So those should kind of balance each other out, but then having a plus 12 and a minus 12 seems like it would send it in two opposite directions. So your kind of spider sense maybe is going off here a little bit, and you're thinking this maybe seems a little fishy. And you should be suspicious. Something is about to go wrong. Nevertheless, let's just sort of keep going, I guess. Let's just like dive in and keep trying to solve this, and let's sort of see what happens. If we don't catch it just at this early stage, if we're just kind of trying to solve this and mind our own business, let's see what it would look like. So let's bring, it doesn't really matter, let's do maybe x's to the left. So let's do minus 3x from both sides, and then let's do numbers to the right. So then we'll add this 12. So the idea is, right, we're canceling here and here, canceling here and here. So 12 and 12 right over here is 24. And then on the left, 3x and minus 3x. Now, 3x minus 3x, here's really where the rubber hits the road, because that's just straight up 0, right? Positive and negative of the exact same term. The x's are gone. The x's are just like out of the problem, just like that. And what we're left with, right, is like 0 equals 24. That just is not true, right? That's just like not possible. This is what we would call an inconsistent equation. Because what happens, right, is when we solve it, essentially what we're ending up with, even if it's not obvious at the beginning, is, right, the same variable terms on each sides, but you're sort of adding or subtracting different values to it. So the variable values are kind of balanced out perfectly, which in theory, maybe that's good. But then the number values are not balanced out. So you're kind of setting one side up to be perfectly in balance, and then you're just very unambiguously skewing the sort of the other values. And there's just no way to make that work, right? Because as you can see, when you try to solve it, the x's just cancel each other. They're gone. And then you're just left with two inconsistent numbers, in this case 0 and 24. These are just not equal to each other. So this is not possible, and there's nothing we can really do about it. We can't really backtrack and try to put in different numbers. There's nothing we can do to change this, negative 12 to a positive 12 to sort of make this work. You could get desperate and say, well, what if I did, -1 and -1, if I multiplied both sides by -1 to make this a positive 12 and to make that match? Well, if you did, then your three x's wouldn't match, and it would be inconsistent for another reason, right? Any kind of move you make to try to fix this is going to come apart. Now, I'm making this sound like it's really bad. It's fine, I guess unless we're trying to solve this equation to create world peace or something, that would be a little depressing. But just as far as like we're trying to find a number in a math problem in algebra class, this is not possible. And so what that sort of means for us, right, is we would call this an inconsistent equation. The way that the book notates this, literally what you can say is there's no solution, right? There's no possible solution. And the way the book kind of notates it is they use this math symbol, which is sort of a 0 with kind of a dash through it. What this means is just a math notation for what we call the empty set, which literally just means a set with no numbers, right? It's like having an empty box or something. So here all the solutions to this equation are in this box, and you open the box and there's nothing in it. It's like a really dumb sort of joke or something. So the homework will kind of use this notation. For me, if you just want to write no solution or something like that, that's obviously also okay. But because we're doing everything through the online system, you're going to expect to see this empty set kind of notation. So that's what it means, and that's sort of when you would use it. So that's an inconsistent equation. So what else could kind of quote unquote go wrong? Let's take a pretty similar version of the equation we just were working with. I'm going to make one little change, and it's going to make a big difference. So rather than doing 3 times the quantity x minus 4, let's do 3 times the quantity x plus 4, and then we'll keep the other side the same. So we'll distribute again. So now instead of 3x minus 12, this is plus 12. The other side, right? 2x, right? 2 is plus 12, and then plus x. So you can kind of start to anticipate what's going to happen here is I've got 3x plus 12 on the left, and then I'm going to match that, right? 2x and x would be 3x here, and then plus 12 comes down. So what's happening in this case is rather than have minus 12 and plus 12 like we did here, we've actually had a new version of this equation where not just the variables are balanced, but also the numbers are balanced. So that's interesting. What's going to happen if I try to sort of shift everything around? So if I maybe do minus 3x from both sides, bring this over, and I'll bring the 12 over as well. So the idea, right, is we're canceling here and here and here. But 3x and minus 3x, just like last time, is 0. But what happens now is I've got plus 12 and minus 12, and I'm going to match the 0 perfectly. So this is a case where I actually have 2 different looking equations, but they turn into and simplify into the exact same equation on both sides. So rather than getting an inconsistent equation, I'm getting, I guess in some sense, the opposite. I'm getting an extremely consistent equation. This, rather than being never true, this is always true, right? I mean, essentially I've come up with this kind of, trivial statement, 0 equals 0, which you'd say, yeah, that sounds right. Rather than the impossible situation I had here with, 0 equals 24, just 2 numbers that are not equal to each other means I don't really have anything I can do about this. 0 equals 0 is always true. But that puts me in a weird spot of saying, okay, well, what's the x supposed to be? And the answer here is literally x can be anything. X here is any number. right? X could be any real number. Any number here would work to solve this, because the idea is, right, both of these sides of the equation are really just the same thing. And so, if, it's like I'm trying to say that, like, x plus 2 equals x plus 2, right? Or I'm trying to say 5 equals 5. That just always is true, kind of regardless. There's nothing I can really do to make that not be true. So it's always true. This is actually what we would call an identity. Rather than being an equation, it really is an identity. It's just two equal things. So x could be any number, and it would always be true. The notation in the book, they do this kind of set builder notation again, as they say, x, where x is all real numbers. So the way you're going to sort of see that on homework, quizzes, and tests, right, through the online system, is with this kind of set builder notation. But the idea is it's an identity equation, right? And you're getting there if you sort of try to solve it and you shift everything around and you end up with this kind of trivial, right, 0 equals 0 end result. You might even kind of pick it out earlier, right, when you get 3x plus 12 equals 3x plus 12. At that stage, because both sides match perfectly, in some sense, you could probably say, okay, I know this is an identity because I'm literally looking at the same equation on both sides. So if you pick it out at that stage, great, that's fine. Then you can kind of save yourself a step. But, for sure getting to the x equals, or rather the 0 equals 0 stage is kind of when absolutely this is an identity. So that's two kind of unexpected results. Typically, again, if we kind of just pick numbers out of a hat, that's a little bit unlikely to happen. You have to kind of work a little bit to get particular setups and kind of hide a little bit that these are the same equations on each side. If we just pick numbers out of a hat, you're probably not going to randomly end up with the same thing on both sides. And anytime you have equations that, aren't the same thing, or where the variables match up, right, either of these two scenarios, if we're just sort of taking a typical equation, we should be able to sort of solve it, do the steps we were doing before, right, distribute, combine like terms, shift the x's to one side and the numbers to the other, divide, and get a solution. That'll be like much more common, and that'll be sort of what we see, 95% of the time if we were just sort of picking numbers out of a hat, even more than that maybe. In any event, that's the deal with linear equations, so sort of your standard stuff, and then also these kind of, somewhat less likely scenarios.